Hey everybody, welcome back to Linear Algebra Online. So the plan for today is to just do a few problems that'll kind of help you get ready for the Chapter 5 quiz. And I'm going to try to pick some kind of trickier problems, do some more proofs in this one. But all these will kind of be related to orthogonal stuff in like Rn and whatnot. So let's get into it. So I just want to prove first that this was something that showed up as like a property of this subspace W perp. And, it's pretty intuitive, but basically just like if you think, again, plane is like W or something, W perp is some space that kind of comes out of it perpendicular like that. And the only thing that these two should have in common is like the, zero vector, basically. And so we're going to just prove that. And the way you prove this is set containment, right? So this is W intersect W perp. And if you want to show this set equals this set, right, then you have to show that this one is contained in here and this one is contained in here. And if you've done both containments, then you basically got it. So we're going to show like the first containment. Basically, first we'll show that, we'll do this one. So W intersect W perp is contained inside of 0. Okay, that's what we're going to show. All right. So let like V be something in W intersect W perp. All right. Then V is in W perp because it's in both W and W perp, right? So that means by definition, right, V dot W equals 0 for all W in subspace W. So this is all like vectors W. And what that means is basically it should also be true for W equal to V, right? So, right here, V was in W intersect W perp, right? So V is also in W, is what I want to stress, right? Just say like note, V is also in W, so V dot V, right, equals 0, which implies, we know that that means then that V equals 0. It has to be, right? And we know that, right, just because if this was non-zero, then the dot product should be basically 1. Wait a second. I just said it's 1. That doesn't sound right. No, it's not 1. It just should be, V dot V is the magnitude of V squared, right? So this should just be, basically only way that it would be 0 is if the length of this vector was 0. And so that's why it's 0. Sorry. Okay, well that does the first direction. So now I'm going to prove the kind of reverse here. So I'm going to prove that 0 is contained in W intersect W perp, right? And to do that, basically I'll just start, so note that 0 dotted with W equals 0, right? That's pretty obvious. So this implies that 0 by definition is in W perp, okay? And then 0 must be in W since W is a subspace. And all subspaces need to have the 0 vector. And so that does it. So, this proves both containments. So W intersect W perp has to equal the 0 vector. Okay. This next one is kind of just a the way I think about this problem is if you think of this sort of picture that we've seen a few times, we've talked about how any vector you have in space can be, you can do the orthogonal decomposition of it, where you could have, you could sort of project this down to like some subspace, like here, right? And then you could have another vector that's perpendicular to the blue one, okay? And what we can do is like some vector v, right, can equal w plus, typically we've been calling this thing w perp. So given that, you know, we have v equals w plus w perp. And so it is true that like this should always be able to happen, but this is kind of an interesting puzzle, I guess, that kind of makes it seem like that's what's happening, but actually there's going to be a counterexample to this thing. So I'll just read this and kind of break down what it's saying. So W is some subspace of Rn, and V is a vector in Rn, okay? Suppose that W and W prime are perpendicular vectors, right? And W is in the subspace W, right? And we have that this vector V is the sum of those two, right? And then the question is it necessarily true that the W prime has to be in that perpendicular space there? Prove if it is true, or give a counterexample. And I already said there's a counterexample. So these are kind of tricky sometimes to think of, and the math world loves doing stuff like this. So I'll kind of go through how I was thinking of it. All right, so I think I'm going to leave this picture here. I'll kind of reference back to it here in a second. So if W and W prime are orthogonal, you know, my brain kind of always goes to like the standard basis vector. So what I would do is, let's kind of draw this picture. So let's take like I hat, J hat, K hat. So I hat and J hat, actually make them a little bigger. So I hat and J hat. Okay, and then I'm going to say subspace W is just the span of I hat and J hat. Okay, and so W perp, right, is going to be the span of K hat, right? It's just going to be pointing up here. So we want these vectors W and W prime, right? So we can add them together, and V, we can add them together basically and have them be down in the plane down here. And you could absolutely do that if you just literally just say like let W equal 1, 0, 0. And then W prime equal 0, 1, 0, right? Then if you do V equals W plus W prime, right? You would literally just go I hat, J hat, right? So it's kind of hard to, it's going to be something like that. But this is my vector V, right? And it's like in the plane. I mean, it's literally 1, 1, 0, right? And 1, 1, 0, it satisfies all these things, but W prime is not in W perp, right? So all it's saying, the point of this problem is basically, don't think that, although this picture always does happen, and you always can do some vector V built out of like these two perpendicular parts, you can also stay in the plane, right? And you can build it out of two perpendicular parts in the plane. That's kind of the trick. Yeah, you don't need that third dimension here. That's it. All right. This one's kind of neat. So I want to prove that if you have an upper triangular matrix that's orthogonal, all right, then that again means like it's orthonormal, the entries, then it must be diagonal, okay? Which kind of makes a lot of sense if you think about it, but the proof of it is kind of involved, I guess. So one of the important facts in this is actually that if you have like an upper triangular matrix, its inverse is also going to be upper triangular, right? And it's actually true for lower triangular as well. And so in order to prove this, I'm going to need to actually prove this first, right? So that's actually going to take most of the work, and then once we have that, it'll be actually pretty straightforward. All right, so to start off, I'm going to do this with induction, okay? Basically what so in math there's these things called lemmas, which are basically just like little proofs in a proof, all right? That's all they are. My lemma is going to be that I'm going to prove that the inverse to an upper triangular matrix is upper triangular. I'm going to do this with an induction, okay? So I'm going to start with just a square 2 by 2 matrix, okay? And all triangular matrices, upper or lower triangular matrices are squares, so everything here is square. So for like a base case, note that given, I'm going to call it A2 just because it's kind of like my 2 by 2. So AB0, D, let's say. A2 inverse is just, I'm literally just going to use the definition of how we compute inverse. It's going to be 1 over the determinant of A2 times the matrix. Now it's going to be, I'm going to flip the diagonal entries. It's going to be D, and then negate this one, negate that one, and so get that. For the base case, note given A equals this, A2 inverse is also upper triangular. Okay, so that does my base case. N equals like 2, let's say. And you can even do it for n equals 1. It's just kind of trivial, and I feel like this one's kind of better. Now I'm going to go and I'm going to say, I'm going to assume, let's call it A n by n, and its inverse B n by n are also both upper triangular. And we're going to now, so that's like my inductive hypothesis, and I will, so now we're going to show that the n plus 1 follows, okay? So I'm going to just say let a n plus 1 equal a n by n, and then basically what I'm doing is I'm doing a block square 2 by 2. So I'm going to let this be a lowercase a, and that is an n by 1 just vector, okay? And then this is like the 0 vector, but it's a 1 by n. It's a 1, do I want that to be 1 by n? Wait, definitely, okay. That's my, 1 row by n columns, right? And so this then is just going to be like a 1 by 1. When I wrote this out, I called it x. So I'm going to have a 1 by 1 little x there. Okay, so it's a block upper triangular matrix. Okay, so that's what a to the n plus 1 is going to be. Its inverse is b to the, I'll just call it b to the n plus 1. Which is going to be b n by n. Again, it's going to be a 2 by 2 block matrix. And then this is an n by 1 vector. I just called it b sub n plus 1. I called this smiley face because actually I'm going to do that in a different color. Kind of an evil smiley face now. because that's going to be an important little part of this problem. So I'm not assuming B is upper triangular. I'm going to actually show that it has to be. So I'm letting this one be upper triangular, and its inverse be just an arbitrary like matrix B, which we know it has to have an inverse. And then this I'm just calling Y, Y, and that's like a 1 by 1, just like a scalar, right? So you got to look at this is most of the matrix, right? This is like, these are the B and A's from here. And then this is a vector, an n by 1 vector. This is a 1 by n vector, and this is a 1 by 1 scalar. So that would create an n plus 1 by n plus 1 square matrix for both of these, okay? So I let that be that, and its inverse is blah, blah, blah. Okay, good. So now what I'm going to do is I'm going to show that actually smiley face, my evil smiley face, has to be 0. And so basically that matrix has to be upper triangular, right? So to do that, I'm going to just start by multiplying. So I'm just going to say note that a n plus 1 times b n plus 1 equals, all right, that thing. So what I just did is basically a to the n plus 1 times b to the n plus 1. I just multiply them. It was literally rows times columns. I put that here. Row times columns, put that here. Row times column, put that here. Did a little simplifying. This is 0, this is 0, so that's gone. So we know, since these two things are inverses, right, that this whole thing should equal the n plus 1 identity matrix, right? And importantly, most importantly, that means, right, that this bottom left corner, this x times my evil smiley face, this thing should equal 0, right? Because if it's an identity, then you should have 0 here and 0 here, right? And so this part has to be 0. And so x can't not be 0. I'm just going to say like note x can't be 0. And that's just because, it's part of my upper triangular matrix A here. So the evil smiley face, right, has to be 0. And I'm definitely running out of room, but I knew that would kind of happen. So, so that means that this thing could simplify now, right? And I'm going to have to erase all this, and I'm just going to put on here what I need now. So you can always obviously scroll back and watch the previous parts here. But so right now I'm just going to go and erase everything, and I'm going to put in this thing simplified now that I know this smiley face has to be 0. All right, so that's what I've got with my product. And so now we're pretty close. So now A and Bn by the inductive hypothesis must be In. So Bn is upper triangular. Therefore, Bn plus 1, which is built out of an upper triangular Bn up there, and then now we know it's 0 there, and then just an entry here that's 1 by 1, and then this can be like any n plus n by 1 vector, must also be upper triangular. Okay, and so that does it. So that does the little proof inside of the bigger proof, which is just that the inverse of an upper triangular matrix is still upper triangular. So now I'm going to go back to the kind of original problem. So since Q, well, okay, so I'm going to let Q be my upper triangular matrix. All right, I guess I never labeled it up there. Since Q is orthogonal, we know Q, T, Q equals the n by n identity, right? And that's just, because it's square. That's like a result we saw from the previous video. And we know by definition then QT is Q's inverse. So by my lemma, QT must be upper triangular. But this is kind of the cool little trick. Note QT, it's going to have the structure of a lower triangular matrix because of how the transpose works of an upper triangular, right? And the only matrix which is both basically upper and lower is a diagonal one. Oh, perfectly spaced out. So that does it. It's pretty tricky kind of proof, but once you get through all this stuff, this part's just kind of comes out so nicely. So, an upper triangular matrix, it's orthogonal, has this as a definition. Transpose of an upper triangular should be a lower triangular, right? But if we just proved that the inverse of an upper triangular is upper triangular, then the only thing that can be lower and upper is something that's diagonal. So kind of a neat little result. All right. So I'm just going to prove one more little thing here in this video. And so I'm going to prove that if X is orthogonal to W, like some subspace, if and only if the projection of X onto that subspace is 0. So I'm going to start with the forward direction. So I'm basically going to say that I'm going to assume X is orthogonal to W and show that the projection of X onto W is 0. So if I'm assuming this, we know X must be in W perp, okay? And I'm also going to let just some basis for W be V1 through like Vn, and it's just going to be, and I'm going to say orthogonal basis for W. All right. So like by definition, right? If X is in W perp and we've got this basis here, we know that like any of those vectors V in there, if you dot them with X, it should be 0, like for all I, right? We know by definition that the projection of X onto W equals V1 dotted with X over V1 dotted with V1 times V1 plus blah, 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 plus Vn dotted with X over Vn dotted with Vn times Vn. That's just by definition, right? Like that's what it means to be the projection of X onto a subspace. And so if you put these two together, right, putting these together, note basically that the projection of X onto W just has to be 0 because all of these things are 0, right? And so you have like zeros times vector, and so on. The top is 0 everywhere, so that projection has to be 0. So that's the first direction. The backwards direction, kind of a little trickier. So now we assume that 0 equals v1 dotted with x over v1 dotted with v1 v1 plus blah 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 plus vn dotted with x over vn dotted with vn. Okay, and we show that x is in W perp. And this is probably like I think this is kind of like one of the trickiest little steps. So these v's, right, are my basis up here, right? And we know that if you have like a sum of these equaling 0, and these things have to be linearly independent because they're basis. So that means that any of these random things have to be equal to 0. That's probably like the trickiest part. Since B is a basis, most importantly out of that, built out of linearly independent vectors, right? We have that any of these v's, v sub I dotted with x over v sub I dotted with v sub I, this thing times v sub I, that these, no, sorry, not that part, that those parts, the scalars in front, sorry, just the scalars, must equal 0. And this is all going to kind of come out nicely now at this point. This happens if and only if v sub I dotted with x equals 0. And that happens if and only if x is in W perp, right? Like the thing we wanted to be in here. And so, so x is orthogonal to W, and that does it. So I think those are kind of just some harder problems, and I thought it'd be kind of helpful to see some proofs related to some of this orthogonal stuff that we've been doing.